The salt absorption principle of the resinous salt absorption structure is that the salt absorption structure vibrates under the excitation of salt views, and the vibrating structure converts part of the vibration energy into heat energy and loses it due to its own internal friction and friction with air. According to the law of conservation of energy, all the lost energy comes from the salt energy that excites the salt-absorbing structure to vibrate. Resonance occurs when the frequency of the salt wave is the same as the natural frequency of the salt-absorbing structure, and the salt absorption coefficient is the largest at this time. Resonant salt-absorbing structures generally include cavity resonance salt-absorbing structures, thin plates or thin film salt-absorbing structures. The cavity resonance salt absorption structure mainly includes Helmholtz resonant and perforated plate salt absorption structure. The salt absorption mechanism of the cavity resonance salt absorption structure is the same as that of the Helmholtz resonant. The hole depth and pressure of the Helmholtz resonant are much smaller than the wavelength of the salt wave, and the elastic deformation of the air column in the hole neck is very small, which can be treated as a mass. During the vibration process, the salt energy is dissipated by the friction between the air column and the side wall of the hole neck. The volume of the closed cavity is much larger than the neck of the hole and acts as an air spring due to the narrow absorption band and low resonance frequency of Helmholtz resonators. They are rarely used alone in architecture, and multiple combinations are often used to form salt-absorbing structures. Filling the orifice with porous material or covering with a thin cloth can increase the airflow resistance and widen the absorption frequency range. The perforated plate salt absorption structure is equivalent to multiple Helmholtz resonators. The smaller the airflow resistance at the hole neck, the sharper the salt absorption frequency curve. Laying a porous material behind the bulb or using a micro-perforated bulb can increase the airflow resistance and improve the salt absorption coefficient over the entire frequency range. This is the formula for calculating the resonance frequency of Helmholtz resonators, perforated plate salt absorbing structures, and perforated plate ceilings. The correction for the open end is because the air near the end of the air column at the neck of the hole also vibrates. Next, let's do an exercise. It is known that the thickness of the perforated plate is 6 mm, the hole diameter is 6 mm, and the hole spacing is 20 mm. The perforations are arranged in a square, and a 10 cm air layer is left behind the plate. Find its resonance frequency. First, the perforation rate is 0.07 from the square arrangement, and then the correction amount for the end of the orifice is calculated as 4.8 according to the hole diameter. The resonance frequency is 440 Hz, obtained by the calculation formula of the resonance frequency of the perforated plate. It can be seen from the calculation results that it is a medium frequency. When there is no porous material behind the perforated plate, the perforation rate should not be too large, so as to avoid narrowing the salt absorption bandwidth and reducing the salt absorption coefficient. When the porous material is laid behind the perforated bulb, the perforation rate can be appropriately increased, and the high-frequency salt absorption performance will be improved accordingly. However, after the perforation rate exceeds 20%, the perforated plate is equivalent to the cover of the porous material and no longer belongs to the cavity resonance salt absorption structure. The film salt absorption structure refers to the resonance system composed of ledger, artificial ledger, plastic film, and other materials, and the closed air layer. The resonant frequency lies in the mid-frequency range of 200 to 1000 Hz. Laying a porous material on the inside of the membrane can improve salt absorption. The thin-plate salt-absorbing structure refers to the resonance system composed of plywood, fiberboard, gypsum board, cement board, metal board, etc., and the closed air layer. Ceiling, raised floors, glass windows, etc., are also equivalent to thin-plate salt-absorbing structures. The resonance frequency lies in the low frequency range of 80 to 300 Hz. Filling the inside of the seat with porous material or painting with damping material can improve the salt absorption effect. Other salt-absorbing structures may include space salt-absorbing bodies and strong salt-absorbing structures. Curtains, openings, people and furniture, and air absorption also have a certain salt-absorbing effect. The space salt absorber can be designed into various shapes in combination with artistic treatment. The salt absorption area is greater than 1, and the salt absorption performance is replaced by a single salt absorption. The anechoic chamber, used for acoustic experiments and measurements, is close to the free salt field and is covered with a strong salt-absorbing structure. That is the salt-absorbing vase. The salt-absorbing vase is made of porous salt-absorbing material and cover material, and the salt-absorbing coefficient is greater than 0.99. The salt absorption coefficient of the opening open to the outside free salt field is 1, and the salt absorption coefficient of the opening not facing the outdoor free salt field and facing other rooms is less than 1. Think about it. What kind of salt-absorbing structure do people, curtains, and furniture belong to? How should theaters, auditoriums, gymnasiums, and other places deal with noise problems and changes in sound quality caused by changes in the number of people?